So my agenda today is to look at practical game AI. So this is the outline of my presentation. So first to look at game software in general, or game engines, for example, AI techniques, more specific on game AI techniques. So these are things that we are going to look at. So when we look at game software, let's say we have a Java program or a C program on one end. And on the other end, we have something like a game that you can play on your mobile device. So what is the difference between any ordinary C program, C++, or a Java program, and a game? You didn't expect a quiz early in the morning. You come all the way to Singapore from all parts of the world. So what is the difference? A game, is it a program? Yes. And it's a little bit more than just an ordinary program. So the idea is like to see what exactly we bring in to bridge from getting from a simple program to a playable game. Let's look at this simple one. So what's our objective here? To take that square and put it onto the other side. So we keep doing this over and over and over again. And this is how it looks like. So which we call as a game software. We have many simple blocks. We connect them together. That's the view of this particular game. So we also try to show this from a software engineering perspective in terms of a sequence diagram. We start, so it goes from left to right, and also in terms of time, it goes from top to bottom. We call this as a sequence diagram. And if you want to capture that same game, the ping pong game, it looks something like this. So this is a view of that particular software. It's a program that has lot of objects or components in it, and each one of this component is linked, or it does something when it runs. Okay, and that is captured in this sequence diagram. So this we can call as an object diagram, and this as a sequence diagram. So what am I trying to say here? So when we take a simple C program and try to make a game, we define this as a game development framework. Some people call it as a game engine, for example, if it's a large engine. So the difference here between one game and another game is there are some components we are going to change, which are specific for a particular game. The rest are more or less likely to stay the same. So if you design a framework, okay. So when we design this carefully, that means we are going to make minimal changes to move from one game to another one, and so on. So where does AI fit into this? And why is it important? AI is expensive to compute, isn't it? Any computation we throw in becomes expensive, especially if you are using a small device, a handheld device. It's even more, we have constrained by the resources that we have. So what do we mean by game AI? And why do we need it in games? So we want to make the game more fun to play, yes? Pardon?
More intelligent for the game?
Yeah, you should make the game look more intelligent for the player to interact with. Anything else? And certain things we don't want to do it manually. We want the computer to do things for us. Okay, and this is where computers are good at. So we want to exploit the power of the computer to help in the gameplay. So as I mentioned, we want to make the computers to do certain tasks that like in traditional AI. So we want the computers to do things for us. So essentially, when we talk about AI, we want to get some superhuman abilities. So it should behave slightly higher than what humans, or better than what humans can do. So this is one of the criteria. And computers have proved successful in playing games as opponents. Sometimes we want to play one against other, and the computers tend to perform well. So many of these problems, like originally, were considered as AI problems. But slowly, we take things out of this list and say, oh, these are ordinary things which can be solved, like search techniques. Traditionally, searching was very, very tedious to do. We said searching is an AI technique. People develop more and more techniques to do efficient search. So we also want to like mimic humans in certain cases. So we run Turing tests to say, oh, this is an AI technique that I've developed that can cheat or mimic what a human can do. So let's move into games and AI. So if you look at traditional Pac-Man, it uses some simple techniques to move opponents around or characters around the environment. There are other places game AI has been used, like Golden Axe is an example. So the key things in game AI is, for example, you want to sense certain things, and the program can sense the environment. That is a non-playing character. It senses the environment and does something in an intelligent way. We also use AI techniques for searching, especially to find a path to navigate the non-playing characters in an environment. We can think of AI in having formation, we have, for example, a flock of birds or animals that you want to move in an intelligent way. So how does this formation work? Let's say we have hundreds of characters or soldiers or birds that have to fly as a flock. So what type of intelligence do we put into the flock? Do we put some collective intelligence, or do we put some tiny intelligence into each one of them? Yeah? Yeah, so each one runs like a swarm, that we have put some little intelligence into each one of them. They perform some action, and based on that, we get a collective behavior, which is slightly different from the individual behavior itself. Like, for example, we want to stay the flock to be close to each other, and we don't want them to collide with each other. We want to steer them in a particular direction. We want to align the velocity and so on. So different rules that help us to create formations. People also work on AI techniques where we can do some emotional modeling. So people want to take this one step further, want to add more complex AI techniques. An example can be like to simulate the human brain. So how easy or difficult is it to simulate the human brain? Here you have some answer, no? So we want to simplify this model, try to create human-like behavior, and neural networks are a good candidate for that. We'll see some example. Bots in first-person shooter games, people take the game AI techniques and then try to design new bots, like as part of the AI techniques, to make sure that we get better performance. We also have seen things go both ways when we take a training simulator, a military simulator, which is used in a simulation environment, which is deployed in a game, or vice versa, take from a game and then make intelligent military simulators out of this. For example, you want to have a racetrack, and you want to move your vehicle around that in an intelligent way. So you are driving in your car, and there are opponents who are competing with you. So we can think of using AI techniques to move the opponent cars or the non-player cars in the environment. So traditionally people use conversation trees, like where you want to have communication or conversation agents in a game environment. The idea here is to have three needs. For example, the ability to move characters or pathfinding, ability to make decisions about where to move, whether to move to the left, right, or forward, and the ability to think tactically or strategically. You can bring in several things into your game to make it interesting. And you will see these are the underlying techniques in most of the AI algorithms that we use. So let's look at some specific ones. Yes? You want to get from one point to another point. Why is it so difficult? Pardon? Yeah, you want to find an optimum route to navigate in an environment. And there can be obstacles in the environment. You want to avoid them. The obstacles can be moving as well. So people develop techniques which are quite common in many games. So the two types of techniques that are normally used in finding a path are to use a grid or a mesh. And then this is your computational mesh. It's an X and Y grid. It's two-dimensional. You compute based on this mesh, and then say you want to go from point 1 to some other location. So you want to move a non-player character. You can move one opponent, you can move a team of them together. In that case, they have to coordinate and then move together. An alternate approach is not to use a mesh, but use the grid, not to use the grid, but to use a mesh itself. So it can be a polygonal mesh, which is not a regular grid. So we have to still find a way to navigate in this particular environment. So in this particular case, the question comes to like where exactly should be the intelligent? Should the intelligent be in the character's head, or should it be in the environment? So where do we put the intelligence? Like in the case of a flock, we said we have one character in the flock, we put an intelligence. And we want to do this for 100 different elements of the flock. That means the intelligence has to be quite small because we have many, many characters to compute within a given time frame. An alternate approach is to put the intelligence in the environment, don't put it in the character. Put the intelligence in the environment, so when the character comes to that particular location, it can sense that and then act in an intelligent way. That's what we all do, right? So you see a traffic light, you know what to do. It says red, we stop there. If we say green, we cross that. So we don't worry about it when we are not near that particular zone. So when we are away, we don't worry about it. So in the case of a mesh, it's in the case of a grid, a 2D grid, for example. So we want to find a path. So we take the grid, and then we compute the mesh, compute the path, and then this is overlaid onto the 3D environment, and then you can move the characters around that. So in this particular example, there are many characters they have to coordinate and then move so that the path can be unique, or depending on the criteria that we specify, we can move them in a nice way so that they don't overlap, for example. So as I mentioned, like when we specify algorithms for finding path, it can be simple algorithms which can be put to navigate each one of the void in a flock. Or on the other hand, it can be adding the intelligence in the environment so that when the character comes to that particular location, it can act in an intelligent way. Let me see if I have an example to show you how this works. So this is an environment that we edit. This is the top view of a street. So if you see a location where it is specified, the intelligence is in the environment, so it's not in individual character there. So when the character comes to this crossing, it senses the environment and then it crosses the road. So this is the editing interface. It's a 2D top view, but there are always people like me who don't follow the rules, so they can cross at arbitrary locations. So what is the advantage of having an intelligence in the environment? Reduce the computation in the character. The character's program is quite small, and it can be easily replicated. You can have one traffic light which is designed well. You can have a traffic light in every intersection or a level or a crossing. You can have this replicated easily in your whole environment. So let's look at, so this is an editor interface. So you can paint the the path in which you want to move these characters. So what we are seeing here is an editor. How do we edit intelligence into the environment? So with very simple interface, now we can say all these characters in this environment have to follow a particular path in this case, or in a particular portion of the environment. So how do we take it into a game engine? You can specify different properties on how they should react. So essentially, this curve is nothing but it's a path in a 3D environment. So there are two things here. One is we want to simulate these characters in a 3D environment, but interacting or editing in a 3D environment is going to be very, very tough. So what we do is we take a projection of that, which is in 2D, in which we can specify this, we paint in that environment. And then we copy it or translate it into the 3D environment. So let's look at genetic algorithms. So what are genetic algorithms? How do they help? So let's say I want to design a racetrack. So we can say a start zone where we want to start, and then this goes around. We can connect several such segments to get a racetrack. And we have a race car. It's a non-player car. And we can put some sensors. I have 3 sensors here. So what it senses is, it's like the front sensor, which is ahead. It says if it intersects the wall of the track, then it says there's an intersection. There's a medium one. This is far away. Okay. So if you see the one on the right sensor says there is an intersection very near. Okay. So in this case, there is no intersection in the near segment. There is no intersection in the medium. Even we may not get an intersection in the further region. Okay. So this tells us something. So how do we use this information to navigate our car around the racetrack? And people use genetic algorithms to do that. So there are several possible directions in which we can move. We can go forward, we can go to the right, left. Sometimes we want to go back as well. Okay. So the idea here is, so given a racetrack, can we automatically move this car or find a track in which, or a path in which we can move this car? And we can use genetic algorithm for that. So what are the information that we need? We need to say, like, we have an inertia in which it moves, and also the acceleration vector. And we use this information, we code this in a particular way, and then use this information to move the car along a particular along a path in this particular racetrack. So the way this algorithm works, so we have one particular path in which we want to trace. Let's say we have another one. That means we can compute a new one or an offspring from the original 2 paths. So the first path may not be a good one. The second path may not be a good one. Maybe an offspring can produce a different result. So we want to find out how to generate a path in which we complete the particular racetrack as one of the criteria, or a criteria in which we don't want to crash with the wall. Okay, so we can specify different criteria, and then we can compute the path. So variation of this is find a child, which is not just a crossover, but we can also add some random elements into this. So this will create, and we run this to see whether it completes the whole track. So here is an example. So we have started from a particular location, then we keep using this genetic algorithm to move the car along this particular track to complete the race track. So what do we achieve here? So now the programmer doesn't have to sit there and say, move the car to this, and this location. It's automatically generated. So if you have one player and you have 2 non-player cars that are racing along with you, so those paths can be automatically generated. So we initially start with a set of such paths, and then we refine this and refine this and refine this until we get a reasonable path. So maybe we can define the one to complete this in the shortest time. That can be one of the criteria that can be used. So let's move to another technique, AI technique that can be used. So the input, so once again, this is an example in which we want to have a car that races through this environment. So there are certain inputs, and we want to minimize certain things. In this case, the skid should be properly controlled. We don't want the car to skid and go off the track. So we have to adjust the steering position, so how the steering is held. We want to adjust the brake, for example, and also the acceleration. So this has to be controlled. So this is how it's specified. So what are the inputs? The input can be, so in this case, we are talking about a decision that has to be made, where based on certain input. So we have distance to enemies as one of the criteria, distance to your friends, the health of the friends, the ammunition, as well as the player's own health and ammunition. So these can be taken as input, and then we process this to get the final output that controls the behavior of the non-player characters. Okay. So the way we do this is we need to iterate over this many number of times to adjust the weights for each one of the node so that eventually we get a better performance or the desired performance. So let's take one step back. So this is how a biological neuron looks like. So we have axons that connect two neurons. There are dendrites through which the signal is processed. And this is what happens in a human brain. So we try to simplify this using a mathematical model. The weights which I mentioned there are given there. So we have inputs, the weights, function, and then we want to minimize or maximize a desired criteria. Then we try to model that as a network. That's one neuron. Now, each one of the nodes here is a neuron, which is taken and put here. So we have a set of neurons here, or layers of them. Given an input, it produces an output that helps to control our object, our car in this case. So let's look at with some specific example. So we said we have a car with 3 sensors. So sensor 1, sensor 2, and sensor 3. One is sensor which looks ahead, one to the left, one to the right. So this is the input that's captured. And then we feed it to these different layers. And then finally, it's going to say, do something with the motors. So we have sensor, one look ahead sensor, one to the left, and one to the right. Depending on these values, we are going to run this algorithm. And then it's going to say, turn to the left or right, so that this can be steered in a particular way that we want. So the way we do this is we train with several samples. So that's what happens here with different possible inputs. And it generates an output that helps to control the particular vehicle. So here we can define the rules on how this has to be, this has to operate. So what the idea here is this can be taken in and put inside your game, where we have a virtual car that's being controlled with a similar manner. So what exactly happens? So we have a neural network that's defined for this particular scenario. So we have a car, we have the different sensors, and what we want to do is we want to have a particular steering to turn to the left or to the right, and also we want to accelerate or not. Okay. So this is step 1. We specify what are the inputs. So how many inputs do we have here? Depends on the number of sensors and how we define these sensors. And the output is, in this case, there are 2 outputs, steering and throttle behavior. The second step is we define a waypoint, a rough waypoint in which we are going to move these vehicles, but they can steer to the left and right, depending on how these motors are moved. And then we come to the simulation aspect itself. So we estimate how many times, like whether it's moving in a particular track, whether it's hits, whether we have to do a corrective action, adjusting the weights. So this is fed into this network. So we run this over and over again to make sure we get the right type of weights. And then we bring it back. There are certain things, like cars, which don't come to the end. It goes crashes. Some of them turn backwards, for example. So we want one path in which these cars go around the particular loop or racetrack that we want to achieve. And this is done over several iterations. And once we have a particular track that's defined or network that's trained, and that can be used for future use. Like initially we start with the training set, and then we put a new vehicle. Depending on the scenario, it's going to move around the particular track that we want to accomplish. So suppose if you have different tracks. So I start with one particular track, I have a different track, and so on. So can I still use the same algorithm? Or do I have to train it one more time for the new track? Your training is for a specific track. So if you're changing the track to a new layout, that means you have to train this all over once again. What about the number of sensors? I started with 3 sensors. Instead of 3, if I have 5 sensors, do you have to train this one more time? Yes. So let's move to the last technique that I want to discuss here on is fuzzy systems. Has anyone used fuzzy system anywhere? No? Yes? Okay. So let's try to see how this does. Maybe before I go to fuzzy, okay, let's look at behavior trees. Looks like the slides are nicely ordered here. So how many of you have used behavior trees? 1, 2, 3. Okay. So behavior tree, what is this behavior tree? It specifies the behavior of a character. So you have a character that intelligence is specified in this particular tree. By traversing this particular tree, the character behaves in an appropriate way. So a simple structure can be a selector. So you come to that particular level and then see which one of them you want to select. And another element of this behavior tree is a sequence. You do this first, then do that, and do that, depending on the input that you have there. So now let's try to build a slightly bigger tree. So for example, you want to enter a room and open a door if it's necessary. So you come at the top. So what's that node called? On the top? Selector. Okay. So you select that, and then you see, then you have a sequencer. So whether the door is open, if it's open, move into the room. If not, the selector says, go, move to the door, open the door, and then move into the room. So we can, now what we have seen is we have taken two of these elements and concatenated this together to form a bigger tree. So you can, so this is even further modified to have one more level to that particular behavior tree. You can keep building this. And this is quite popular with Unreal Engine, for example. So this is one particular tree here, which is where you can use to define a character's behavior. So I'm not sure if this works. Maybe you can just quickly try this one. So you see the non-player characters which are around there. So this you can use a behavior tree to specify the behavior of all the characters that are in that environment. So this is a player, and all the NPCs, they run their own behavior tree to interact with this player. So the tree can grow rapidly, and it helps to specify the non-player character's behavior. So people in robotics, they found this quite interesting. They said, well, let's take this tree and then use it to control robo. So here there's a robo there. Its behavior can be controlled using the same behavior tree, which is quite popular in games. So the robo can get up, walk, grasp some object, throw it, and so on. So how is that behavior specified? You see something like this. You give it to a computer program, it will get confused. So this is how the behavior is specified as a paragraph. And I try to go into that and capture certain things. Capture the scenario, stand up, walk towards, grasp. If a grasp succeeds, then do something, and so on and so on. And then even more information, and this is translated into a behavior tree, which is not so ambiguous like the previous paragraphs. So we start with a behavior that's defined, and then we capture it as a tree. Once this is there, we give it to our computer programmers, say, traverse this tree, and that runs the behavior of the particular robo in this case. So you can edit them, you can expand this, you can add more behavior or different behavior as you go along. So let's look at one more example here. We have a flying robo, and this is in this environment, and it has to fly and then go through that window in the far wall there. Okay, you release it, it has to find a path and move out of this environment. And a behavior tree is used to specify this. So when it is released in the middle of the room, in one particular case, it finds a path, it crashes into the wall. That's not what we want. There's another scenario, it navigates, and then finds the door, and it exits. And people use genetic algorithm for this. Once again, try variations of the path. So you start with 1 or 2 initial paths, or maybe 10 paths. From that, you can generate hundreds of new paths, and then you try to find out which path is suitable. So in this particular case, we see so many different paths that are traversed. So we use a GA to traverse that. So we have behavior tree, we have genetic algorithms. Eventually, we want to find a path for this particular object to get out of this environment. So which is the best path here for the flying robot to get out of the room? So the objective here is it should come out of the room which is equally distant from the wall. So which goes through the center of the one is considered as the best in this particular scenario. Okay. So you find a path so that you can move out without hitting the edges. So let's move to fuzzy logic. Fuzzy logic has been used in many games. So what is fuzzy logic? So like, for example, we take the people in this room, measure the height. We can say we can have some crisp values here, okay, well-defined values. So height is in centimeters. But we want to make some decision based on a combination of this. Let's say somebody is tall and strong, or things like that. So in that case, we need a fuzzy type of system. So when we say a crisp, we can say a person is tall or not. So anybody who's tall, we say it's 1. If not tall, we define by 0. On the other hand, in the case of fuzzy logic, we provide a degree of membership in the range 0 to 1. So if it is 0.0, that means the person is not really tall. 1 is definitely tall, and everybody else is in that particular range. So like, for example, Stephen is 0.06 tall, okay, and so on. And this helps to make some decisions in our games. So in the case of a crisp set, so anything is tall is like a step function, whereas in the case of a fuzzy set, it can be a smooth curve. So people use different curves to define the particular set, a fuzzy set. So let's look at one example here. So I have one more car there on the top, and then we want to move this car along this particular track, and we want to use fuzzy set for this. So how does this work? So we define a membership function. So this is a track. The car wants to find that it stays on the track. So if it is white, that means it's off the track. Is that right? If it's dark, that means it's on the track. If it's something between white and dark, the average value is between white and dark. That means you need to do some corrective action. Okay. So you're going along this track. You see something gray, then that means you are not on the track. You have to adjust yourself, and then you have to move around the track. So step 1, you define the track with its sensors. Then we define membership function. So in the previous case, I said that membership function can be a smooth curve. So here we are defining a membership function, which is more like a trapezium. Anything within this is part of this particular set. There's another set which is defined as a triangle. There's a third set which is something slightly different on the other side. So people have variations of these sets. And then a combination of that can be used. So in this case, we have 2 sensors. One is on the left and one is on the right. So a left sensor and a right sensor are there, which helps to capture the data. So the step 3 is you keep doing this loop over and over and over and over again. So within this particular thing, so we read the input. We calculate the membership, whether it's part of the which set it belongs to. Then we apply certain rules to combine certain things. Like, for example, the left sensor says the value is here, and the right sensor says the value is here. So what do we do? Or the left sensor says the value is here, and the right sensor says value is somewhere there. So how do we interpret that? So that's what happens here. And once this is computed, we then map it to a crisp output so that controls the motor, how many degrees we have to rotate to the left or to the right. So the set functions that we do in fuzzy logic is slightly different from our standard sets, like A union B is slightly different in the normal set theory that we use. as compared to the fuzzy logic sets. So as you can see here, it's like, for example, a minimum function is used. So these are some references that you can take a look at. Okay. So to summarize what we have seen here, the idea is to introduce you to some concepts that are used in game AI. So people who are already familiar will already know more about this, but those of you who are new to this topic will have something more to read when you go back. So thank you very much.